In this video we are going to solve problem 2.12 from the chapter 2, the working fluid, from the book Applied Thermodynamics by TD Eastoper and MocConky. Statement of the problem is: a quantity of a certain perfect gas is compressed from an initial state of 0.085 cubic meter 1 bar to a final state of 0.034 cubic meter 3.9 bar. The specific heat at constant volume is 0.724 kilojoule per kilogram per Kelvin, and the specific heat at constant pressure is 1.020 kilojoule per kilogram per Kelvin. The observed temperature rise is 146 Kelvin. Calculate the specific gas constant R, the mass of the gas present, and the increase of internal energy of the gas. So first of all we will write the given data. We have given the initial state and the final state. 1 is used for initial state while 2 is used for final state. So V1 is 0.085 cubic meter, P1 is 1 bar, final volume V2 is 0.034 cubic meter, pressure P2 is 3.9 bar, specific heat at constant volume is, that is the value of CV is 0.724 kilojoule per kilogram per Kelvin, and the value of specific heat at constant pressure is Cp is equal to 1.020 kilojoule per kilogram per Kelvin. The observed temperature rise is T2 minus T1 is 146 Kelvin. We are required to find 3 quantities in this problem. First, specific gas constant, which is R. Second, the mass of the gas present, M. And third, increase of internal energy of the gas, that is U2 minus U1. So to find the value of R, starting the solution, the relationship R is equal to Cp minus Cv can be used. So we also know about the values of Cp and Cv. Just putting these values in this expression and you will find the value of R. So Cp value is 1.020 and the value of Cv is 0.724. So subtracting it, you will get the value of R, and it comes out 0.296 kilojoule per kilogram per kilo. So this is the required solution of part 1. Second, we are interested to find the value of m. So to find the value of m, we can use the expression P1 V1 is equal to mr T1. So it is, when we rearrange it for m, we will get the expression m is equal to P1 V1 over r T1. So let's suppose this is expression A. Here P1 V1 and r are known to us, but the value of T1 is unknown. So first we will find the value of T1, and after that we will use that value in this expression, and then we are able to find the value of n. So let's first find the value of T1. So for that we will need the state equation 1 and state equation 2, just like in previous problem 2.11. We will have final expression for T2, and this expression can be used to find the value of T2 first in terms of T1. So directly using that expression, T2 is equal to P2 V2 over P1 V1 into T1. So if we put the values, P2 is 3.9 bar, V2 is 0.034, P1 is 1 bar, V1 is 0.085 cubic meter into T1. Because we don't have T1, we are interested to find its value. The value of T2 will come out in terms of T1. So T2 is equal to 1.56 times T1. So now we know that the change in temperature, that is the rise in temperature, T2 minus T1 is equal to 146 Kelvin, as it is stated in the problem above, that the change in the rise is 146 Kelvin, represented by T2 minus T1. So here, if we replace T2 by 1.56 times T1, so we can write it like this: 1.56 times T1 minus T1 is equal to 146. Now it's easy to find the value of T1. So T1 is equal to 146. 1.56 minus 1 is 0.56. So the value of T1 comes out 261 Kelvin. Now using this value of T1 in the above expression A, all other quantities are known to us, so expression A will become m is equal to, directly putting the values, m is equal to P1 is 1 bar, converting bar into Pascal, into V1 is 0.085 cubic meter, The value of R is calculated above, and it is 0.296 kilojoule per kilogram per Kelvin. Also converting it to joule per kilogram per Kelvin, we will multiply 10 to the power 3, and the value of T1 is calculated over here. It is 261 Kelvin. So if we simplify this, the value of M comes out 0.11 kilogram. So this is the required solution of part 2. Now to find the value of rise in internal energy or increase of internal energy, for that again we can use the expression used in problem 2.11, but this is only internal energy, not specific internal energy. So for internal energy U2 minus U1, we have the expression equal to M CV T2 minus T1. So if we put the values, U2 minus U1 will be equal to M value is calculated, that is 0.11. The value of CV is given to us, and it is 0.724. Temperature rise is 146 Kelvin. So if we simplify this, the increase of internal energy is equal to 11.63 kilojoule. So this is the solution of part 3, and this is the overall solution of problem 2.12. Thanks for watching. Please like and comment on my videos. Also subscribe my channel to get new videos.